This is the first review video for Test 1, and it covers material and example problems on functions and graphs. In our first example problem, we're given a relation or a set of ordered pairs, and we're going to determine the domain of this relation, the range of the relation, and we're also going to determine whether or not this relation is a function. So remember that the domain is going to be all x values, and the range is going to be all y values. So for this relation, our domain is going to be 12, 20, 39, and 51. Now remember, we only list each value once, so even though 12 appears multiple times in the relation, it only gets listed once in the domain. Our range, which is, like we said, all y values, would be 3, -9, and 5. In order for this relation to be a function, we would need each element in the domain to correspond to only one element in the range. However, we can see with this relation that 12 corresponds to more than one number in the range. We have 12 corresponding with 3 and 12 corresponding with 5. So this relation is not a function. In this second question, we're given a graph, and we want to determine whether or not the graph depicts a function, and we're also going to determine what the domain of the graph is and what the range of the graph is. So whenever we're working with a graph and we want to know whether or not it's a function, we can perform the vertical line test, where we draw vertical lines through the graph. And if the line crosses the graph in more than one point, we know that's not a function. So here we've drawn our vertical line in blue, and we can see that it's crossing over the graph at more than one spot. So we know that this graph is not a function. Next, we're looking at the domain. So the domain is going to be all x values that the graph covers. So we can see that the graph begins on the x-axis at x equals -2. And it hits the point of -2, so it's going to be a bracket, so it's inclusive from -2, and the graph will stretch out to infinity. Next, we're looking at the range, and we can see from these arrows that the graph is just going to continue extending up and down, and that the y values will run from -infinity to infinity. In our next question, we're given y plus 2x squared equals 3 minus 2x. And first we want to solve for y, and after that we're going to evaluate the function at x equals 3. So first, in order to solve for y, we want to move all of our x terms to one side and keep our y on the other side. So the first step to doing that would be to subtract 2x squared from both sides. That's going to leave us with y equals 3 minus 2x minus 2x squared. If we were to rewrite that in the correct form, it would be -2x squared minus 2x plus 3. To evaluate this at x equals 3, we're going to take our equation and we're going to plug the 3 in for each x in the equation. So f of 3 would be equal to -2x, or 3, squared minus 2 times 3 plus 3, which simplifies to -18 minus 6 plus 3, which is equal to 21. In this question, we're given a graph, and we want to determine the intervals on which the graph is increasing, on which it's decreasing, and where the graph is constant. So we're just going to work our way from left to right. So first we're going to look at this part of the graph right here, and we can see that as our x value is increasing, our y values are decreasing. So we know that on this interval the graph is decreasing. So this interval runs from -infinity, and then it stops at x equals -2, and it hits the point, so we're going to use a bracket to end that interval. This next part of the graph, right here, we see that as the x values are increasing, the y values are remaining the same. So this part of the graph is constant, and it runs from x equals -2 to x equals 2. We see these open-ended points, which means that we need to use parentheses in our interval. So we have that the graph is constant from -2 to 2. Finally, we're looking at this portion over here on the right, and we can see that as the x values are increasing, the y values are increasing as well. So this portion of the graph is increasing, and it begins at x equals -2 with a closed point, so we're using a bracket. So from x equals 2 to infinity, our graph is increasing. In this question, we're given a graph, and the first thing we're going to want to do is define it as a piecewise function. And then after that, we're going to define the domain of the graph, and we're going to find the range of the graph. So remember, when we're working with a piecewise function, we're defining the function on different intervals of x. So we have two different pieces of a graph here. We've got this one over here on the left, and then we have this other portion here on the right. And we're going to want to define each of those lines in terms of the interval of x that it runs along. So over here on the left, we have a straight line at y equals 2, and it's running from -infinity and stopping at x equals -1. So we know that f of x is equal to 2 whenever x is less than or equal to -1. And we say less than or equal to because the line actually hits that point. So that's going to be the first rule of our piecewise function. Then here on the left, we see an open-ended point at x equals 2, and then a straight line running at y equals -1. So here we have f of x is equal to -1 if x is greater than 2. So here we've created the rules for our piecewise function, and as previously stated, they're based on intervals of x. For the domain of this graph, it's important to notice that the graph doesn't cover all values of x, so we're going to need to use the union of two different intervals to define this domain. So the first interval, we can see, runs from -infinity to -1, and we know that it would be a parenthesis at the -infinity and a closed bracket at -1. So we want the union of that interval with 2 to infinity. So that defines the domain of our graph. And the range, the y values, we only see two different y values. So this isn't going to even be expressed as an interval. It's just going to be a list of two different values. We see y equals 2 and we see y equals -1. And so that is going to be the range of our graph. In this question, we're given a piecewise function that describes a patient's blood sugar level in terms of t, which is the hours since an insulin injection was given. So we have 40t plus 105 if t is greater than or equal to 0 or less than or equal to 4. F of t, or the blood sugar level, is 265 if t is greater than 4, less than or equal to 11. -75t plus 1090 if t is greater than 11, less than or equal to 14. And the blood sugar level would be 40 if t was greater than 14 or less than or equal to 24. So the question here is, if a patient was given insulin at 5 a.m., what would their blood sugar level be at 11 a.m.? So in order to do this, we first need to figure out what our t is going to be. So if the insulin injection was given at 5 and we're taking the blood sugar level at 11 a.m., that means that 6 hours have passed since the injection was given. So t equals 6. So with the piecewise function, in order to find our solution, we have to figure out what interval our value falls on. So t equals 6 falls in this second interval right here because 6 is between 4 and 11. So we know that at 11 a.m., or f of 6, the blood sugar level of the patient would have been 265. Next, we want to know what the patient's blood sugar level would be at 6 p.m. So at 6 p.m., 13 hours have passed since the insulin injection was given, which means that T equals 13. So for this question, our time falls in the third interval, which is between 11 and 14. So we're evaluating f of 13 to figure out what the patient's blood sugar level was at 6 p.m. So we're going to say negative 75 times 13 plus 1090. And using a calculator, we can see that that is equal to 115. So the important thing with this question is realizing that because the injection was given at 5 a.m., 5 a.m. is pretty much what we have for t equals 0. So that's t equals 0. And then from there, we're counting up by hours to figure out what our t value is, which is why at 11 we have t equals 6, because 11 a.m. is 6 hours after 5 a.m., and for 6 p.m. that's 13 hours after 5 a.m. So it's important to make sure that you're correctly defining your variable and then also correctly identifying what interval it falls between. In this question, we're given half of the graph of y equals f of x, and we're asked to figure out what the complete graph would look like given that f of negative x is equal to f of x for all x. So keeping this rule in mind, we're going to be able to figure out what the other half of this graph looks like. So from this graph, we can see that f of 1 is equal to negative 1. So if we know f of 1, with our rule, we also know then that f of negative 1 is equal to negative 1. So we can plot that point on our graph. We also know that f of 3 is equal to 3, which means that f of negative 3 is also equal to 3. We can plot that point on our graph as well. So basically, from these points, we kind of get the idea that when f of negative x is equal to f of x, that just reflects our graph across our y-axis. So we can use our rule to plot some new points on the other side of the axis, and then we can just connect our dots to complete the graph. In summary, we have the domain, which covers all x values of a function or graph. The range is going to cover all y values. With interval notation, we can either use brackets or parentheses, where brackets are inclusive of a point and parentheses are exclusive of a point. We also took a look at piecewise functions, which are functions that are defined on different intervals of x. So this video covered a variety of sample problems, and you can find more in the non-credit customized Test 1 review. There will also be 2 more videos to review for Test 1, and they will cover operations on functions, composition of functions, as well as trig functions, evaluating trig functions, and solving for right triangles.